Checking 1, 2, 3. Right, it's good. Right. Probably you see I post the homework for chapter 8, or the first part of chapter 8, and the test review. The test review pretty much will be similar question on the test. However, the test is different than the homework. I'm going to post a sample test later, so we'll see what a test will look like. But what I try to is, if we have time, I plan to do that online for the test review, or any homework question. I want to dedicate some time to do that. It may or may not be on Monday, Wednesday, and Friday. It may be on, let's say, on Saturday, for example. But yeah, I plan to have some time to do the test review or answer some homework question. But that will be later of the week. Right now, we'll continue from what we have from last time. As always, if you have any question, please put on the chat. Right. Now we continue from last time. So on section 6.2, 6.3, sorry. And we did this example 5. Let R be bounded by y equal to e to the x, y equal to 1, and x equal to 1. Set up the integral. That calculate the solid generated by revolving the region R about the x-axis. Right. So real quick, we try to graph y equal to e to the x. And then y equal to 1. We cannot really do x equal to 1, but let's see the graph. Right. I'm going to zoom in. sorry. It should be zoom box, zoom number 1, right? Right. And then second zoom, turn the grid on, right? That's better, right? And so y equal to 1, e to the x, and then x equal to 1 is going to be here. So let's sketch that. Right, e to the x. When y equal to e to the x, when x equal to 0, e to the 0 is 1. When x equal to 1, e to the first power is e, and that is about 2.71828. So it is kind of like that. And then y equal to 1. And then x equal to 1. And we talk about that region or right. And it rotates about the x-axis. Right. So if it rotates about the x-axis, meaning that we're going to cut the x-axis into little increment. So about the x-axis, we're going to use dx. And if we rotate, there will be the hollow region here between the axis of rotation to the edge of the region. So that is going to be a washer method. And then some limits. Right. So first, determine the big radius. The big radius is from the axis of rotation, the x-axis, to the outer edge. So if this is the region R, we go from the axis of rotation here to the outer edge of the region, the furthest possible point away from the axis of rotation. So that is the big R. So in this case, it is just going to be the function above by e to the x and below by the x-axis. So we just say e to the x minus 0 if you want to. Which is good. and then the little radius. Little radius will go from the axis of rotation to the inner edge, and that is little r, which is from 0 to 1 by y equal to 1, so this is 1. So to find the volume, it is going to be pi, the big area, the big radius square minus the little radius square and the limit for x go from 0 to 1. Right. If we rewrite this, we can say from 0 to 1 pi e to the x square, e to the 2x, x and 2 times together minus 1 dx. Right. So that is the volume if we rotate about the x-axis. Next, what if we have the same thing but rotate about the y-axis? Right. I'm going to draw this one again. Now we have the same region R but rotate about the y-axis. Right. Now if it is rotated about the y-axis, we're going to have to cut this along the axis of rotation. So this is going to be dy. And also there will be something in between the axis of rotation and the edge. So in that case, it is the washer method. Right. Now, the limit for y. So in terms of y, the limit will go from 0, from 1 to whatever this point is. And since the function is y equal to e to the x, this one is e to the first, or just e. So the point here, x equal to 1, y equal to e, and so the limit will be from 1 to e for y. Yeah, from here to here. The big radius from the axis of rotation. So So we go from here, axis of rotation, and any point between 1 and E. We go to the outer edge, the furthest point away from the axis of rotation, and so that is the big radius. So in this case, this is going to be 1, x equal to 1. And the little radius it is go from axis of rotation to the inner edge. So that is little r. Right, but we're not going to write e to the x because it has to be in the function of y. So it should be y. So it's not e to the x. So y equal to e to the x. We have to write equivalently y equal to e to the x. If we take ln on both sides, and it cancel out. So we have ln and e cancel out. We have x equal to ln of y. So this function is equivalent to x equal to ln of y. We have to write that as a function of y when we use dy. So the little radius is going to be ln of y. And put them together, we have the volume pi. The big radius is 1. And the little radius is ln of y. Right. So this is 1 e pi 1 minus ln of y square. We cannot do anything with this dy. Right. So that's how we set it up. Right. So about the x-axis. So this is the volume by slicing. So we slice the axis of rotation. If the y-axis is like that, when we slice, we're going to cut that into little pieces, and each one of them is going to be dy. If we slice in the x-axis, we cut in the x-axis, and each one of them is a dx. So this is the volume by slicing. Next, now this will be interesting. Right. Let the region R be in the first quadrant and bounded by y equal to x squared and y equal to x. Find the volume if the region R is rotated about the axis x equal to -1. Right, this van point. Right, so this is easy. The graph y equal to x squared and x. So x squared and x. So we talk about very small region here. Right. So graph should be easy. Right. Y equal to x squared and then y equal to x. That's simple, right? Now, the problem is it is rotating about the axis way over here. X equal to -1, which is the vertical line. And it rotates about that axis. Right. Now, the region here, this is simple. When x equal to 0, y equal to 0, and xy equal to 0, so we have the point 0 and 0. And the point here is 1 and 1. Right. And we're talking about this region here. Right. Now, first of all, we have to determine, is this going to be a dy or is that going to be a dx? Notice that this is rotating about the axis x equal to -1. Now, if we use the region by slicing, we're going to cut the axis rotation into small pieces. That's what we call slicing. So we slice the axis of rotation. So it's going to be like this. Of course, if we stack, it's going to be like this. This is going to be a dy and not dx. So the volume about this axis is v equal to pi r big R square minus little r square dy. Again, we slide the axis of rotation, and when we slide it happens to be vertical, so dy. The limit for y is easy, since we go from 0 to 0 and 1 and 1, so limit will go from 0 and 1. Right. Now, just need to determine the radius, the big radius, and the little radius. The big radius is going from the axis of rotation to the outer edge. The furthest point away from the axis of rotation to the region. So that is the big radius. Now, if we set it up, it is going to be from that function to here. By the way, since we're using dy, everything has to be as a function of y. So y equal to x squared is equivalent to x equal to square root of y. And y equal to x, obviously, is the same as x equal to y. So we when we see that the problem is dy, we have to use the function in terms of y. So we convert everything into the function of y. Now, the big radius, axis of rotation from here all the way to down to h, square root of y. So just like set up the region, it's going to be from the right minus from the left. So square root of y minus a -1 or equal to square root of y plus 1. So that is the big radius. From the function on the right minus the function on the left. The previous example, we don't have to do anything because it's just like ln of y minus 0. Now because this has some other values. Right. Similarly, the lead radius from the axis of rotation to the inner edge. The inner edge give us on the right y equal to x or x equal to y, and on the left x equal to -1. So the right y minus the left, so that's just y plus 1. And put those two together into the graph, into the formula. Integral from 0 to 1 pi square root of y plus 1 minus y plus 1, y plus 1. So this problem is different, that it rotates about the axis, that is not the x-axis or the y-axis. So in that case, we have to find out what is this distance. And just like the region between curves on the right minus 1 on the left. Right, 2. Now we do the same thing, but this time it rotates about the y equal to 2. So I'm trying to draw this again, slightly smaller. That's fine. That's about right. Right. So we have 1, 1, and 2. That y equal to x squared y equal to x. The points 0 and 0, 1 and 1, and the axis of rotation this time y equal to 2. Right, now once again, this is the volume by slicing. So this is the axis of rotation. We're going to slice the axis of rotation. When we do it like that, obviously this is going to be dx, because that is horizontal. And dx, the region from 0 to 1 for x. That's easy. Now we determine the big radius and the little radius. And just a reminder, the video is in 1080p, so if you can change that to the higher resolution, it will be easy to see. Right. So big radius will be from the axis of rotation on to the outer edge. So axis of rotation is here. So we go from there to the outer edge. So that is the big radius from the axis of rotation to the outer edge. If we set up the limit, it is bounded above by that, which is 2, and it is bounded below by y equal to x squared. So above is 2 minus the 1 below x squared. Yeah, to just that. Big radius. And the little radius from the axis of rotation to the inner edge. And so that will be bounded above by 2 and below by x. So just 2 minus x. Right, and then put in that. Two minus x squared is the big radius. 2 minus x is the little radius. Right. And we're just going to leave it like that because we just want to set it up. So it is very important we have to be able to draw this out and then determine the radius, the big radius, and the small radius. And either the top minus the bottom, that's the distance, or the right minus the left, give us another distance. Right, D. Let R be in the first quadrant. In quadrant 1 and bounded by x equal to y squared and x equal to 1, x equal to 2, and the x-axis find the volume if the region R is revolved. The first one about the axis y equal to -1. We don't need this about. Now, the problem is x equal to y square. It would be nice if we write its term of y equal to something x. So first, x equal to y square. We did many problems like this already. Take the square root on both sides. X, y equal to plus or minus square root of x. Right? Take the square root on both sides. And since this is in quadrant 1, we only take the positive values. Just square root of x is that. So we're going to draw y equal to square root of x. Y equal to square root of x. Let's make a little table. X equal to 0. Obviously y equal to 0. 1 square root of 1. Still 1. When x equal to 2, square root of 2 approximately equal to 1.417, or let's say 1.4. So that is about 1.5. All right. So x equal to 0, y equal to 0, 1 and 1, 2 and 1.4. This is y equal to square root of x, or equivalently x equal to y squared. And then x equal to 2 is the vertical line at 2. And then the x-axis. And the x-axis. So obviously we're talking about this region here. Rotate about the axis y equal to -1. That is 1. So -1 is here. And y equal to -1. And it is rotate like that. Right. Now, rotate about this axis of y equal to -1. And we're going to chop or slice the axis of rotation. So when we do that, obviously, that is going to be dx. So the problem is going to be from 0 to 1. I'm sorry. For x, it's going to be pi big radius square minus little radius square and dx. And x go from 0 to 2. Yeah, that is the region R. Right. And then it's easy. Determine the big radius, little radius. from axis of rotation to the outer edge, the outer function. So we're talking about that is the big R, the big radius, the function above, y equal to square root of x. We use the function in terms of x, so it's square root of x. That on the top. Subtract the 1 at the bottom, y equal to -1. So r equal to square root of x plus 1. Let the radius axis of rotation to the inner edge. And the inner edge is going to be 0 because that is y equal to 0 on the x-axis. Minus -1. Once again, the function above minus the function below. But 0 minus -1, so that's just 1. So that makes perfect sense because that is constantly equal to 1. The small radius. Right, so we have the volume from 0 to 2 pi square minus the square dx. The big radius square root of x plus 1, and then the smaller radius just 1. Right. Next, we do the same thing, but it rotates about the axis x equal to 2. So I'm going to draw the same thing, but this is about x equal to 2. Zero, 0. Yeah, I'm plot on those points. 0, 0. The axis first. 1, 2, 3. 0, 0, 1 and 1, 2, square root of 2. Right, and then the region bounded by y equal to square of x, or x equal y square, and then x equal to 2. And then the x-axis, yeah, I'm going to draw all the boundaries here. X-axis y equal to 0. Right. So once again, of course, nothing new here. Right. Let's write out the point. Here, of course, is 0, 0. And the point here, when x equal to 2, y equal to square root of x. So we're talking about y equal to 2 square root of 2 here. So those points. what we have is rotate about the axis of rotation, x equal to 2. So it happens to be about that. Now, what we do is the axis rotation. Now we slicing the axis of rotation. If we're slicing like that, it's going to be vertical. Therefore, it is going to be dy. So we know that our problem is going to be dy. Got the pi here. Big radius square minus little radius square. Now in terms of y, the limits for y for the region going from y equal to 0, y equals square root of 2. Now, big radius and little radius. The big radius from the axis of rotation to the outer edge. So it's like that. Now, the region, it is bounded on the right by the vertical line x equal to 2. So we start from 2 minus. Notice that it has to be a function of y. So we're going to use only the function of y here and not using that one. Now, on the right minus the function on the left. So it's going to be 2 minus y squared. Right? On the right minus on the left. And then the inner radius from the axis rotation to the edge. In this case, the inner radius will be 0 because the axis of rotation is the boundary of the region. So r equal to 0. So in that case, we just have the big R square. So we just have v equal to 0 to square root of 2 pi, and then just r square. There's no little r because the boundaries and the axis of rotation are the same. In that case, we don't have the small radius. And what we call here, this is just this method where there's only one big R. When R equal to 0 here, this is called this method. Going to be this method where there's no small radius, right? So I make this problem like that intentionally, right? So the way we determine the radius is not going to be the function f of x or g of x, or it doesn't matter. It is whatever the distance is, the distance from the axis of rotation to the outer edge, the furthest distance away from the region to the axis of rotation. And it could be on the right minus the left, the top minus the bottom. Whatever the radius is, it has to be positive. So that's why we have the right minus the left, or the top minus the bottom. Right. Now with that, we go to the next section, formed by shells. Why the radius equal to 0? Yeah, because r equal to 0 whenever the boundary and the axis of rotation are the same. So axis x equal to 2 is the same as one of the boundary. So in that case, r equal to 0 because there's no hollow region. So this method, so we say boundary is the same as the axis of rotation. The axis of rotation. And that gives us r equal to 0. Yeah. So just like this problem, if it is rotating about the x-axis, then that will be this method, r will be equal to 0. Yeah. If it rotates about this axis, the little r is going to be equal to 0 because that is one of the boundaries. Yeah. Maybe go back to the beginning of the problem when we have this method. You see on this one rotate rotate about the x-axis. The bottom, the axis of rotation is the same as the boundary, so that's why we only have the big R. If we have a hollow region, then it's going to be the washer where there are two radii. But if the boundary is the same as one of the axis of rotation, then that is just going to be this method with one radius. Right. So what we have is called the disk or the washer method, or in general volume by slicing. Next, section 6.4, it is the volume by shells. First, the shell method. Right, before we go to the shell method, I just want to do this real quick for the previous section about the volume by slicing. So let's say I'm going to draw the volume of something like this. Right. So we have that volume, axis of rotation, like that. Rotate about this. Now what we did earlier is called the volume by slicing. So we're going to cut so called the slicing. So we cut the x-axis and we have cross section like that. Since we're going to cut the x-axis, the width of this line is going to be dy if it is vertical. And then we have a slide. If we zoom this out, it is a cylinder. And the volume of the cylinder is just V equal to pi r squared. That gives us this area of the base times the height, which happen to be dy. And then we just add a bunch of them up. So that is volume of one slide and then the volume of the whole thing, we just add all of them up. Right, so that is the volume by slicing. We just cut one slide, and that one slide, the shaft of a cylinder, and this is the formula for the volume of one cylinder, and add all of them, all of the cylinders. We have the volume by volume by slicing. So this is what we call this slicing. Either this or the washer method. In this case, still will be this method. So that's what's good. Now we do the same thing, the same region. Sorry, that was terrible. And still rotate about this. Now this time we do not do the chopping or slicing like we did earlier. This time what we do is called by shell. So think about this. Instead of cutting this is the axis of rotation. It's better. Instead of cutting, slicing the axis of rotation, what we do is we do the graph around the axis. So the shell is a bunch of layers graphing around this. So what we do is, this will be difficult to draw, but I said we're going to take one slice. This is, I'm not talking about the whole cylinder, we only talk about the surface of the cylinder. So this is one slice. And then of course we can also take the bigger slice, the bigger shell, that is. So we're talking about a bunch of shells like this. Again, I'm not talking about the whole cylinder, I'm talking about the shell, and it is very thin shell. Now, notice we do not slice the axis of rotation anymore. We're wrapping around it. So the width of a shell is very small, and it is going to be the shell is going to stack away from the axis of rotation. So this is going to be dx and not going to be dy, because we just wrap around it, and one shell, and then just another one, and just another one. So this is a very thin shell. And we'll try to find the volume of this shell. Very thin shell. This is not the whole cylinder. It's just a very small, very thin edge cylinder. Right, how do we find the volume of one shell? And then we add all of them up. So the volume of one shell, let's say there's a radius, and then so will still be the height. And the very small one is the dx. Actually, I should write something on the note. Now we take one layer very small. So there's the radius, the height, and there's the width. This case is going to be dx because the shell is going to be from inside out, and it's going to be dx, or the width. Those are three horizontal lines that mean identically, or we define that to be the width. Right. So how do we do this? Now what we see in the note, we're just going to turn a shell like this, and we unroll that into a rectangle. So remember, it is kind of like we have a rectangle, right? When we rotate that, it will be a shell. Yeah. So not only we have the radius of a shell, we also have the thickness of a shell. So that is extremely thin, which is the width of the paper here. So the volume of a shell in a shell like this, or if we roll it out, it's going to be just a rectangle with the width like this. So we can find the volume of one shell, and we just grab another shell around it and another shell around it, and we just do it like that until we have the whole thing. So this, of course, we roll that into kind of a rectangle, and here's the circumference is equal to 2 pi r times the h, and then there's the width, of dx. So length times width times height, or 3 dimension. So volume of the shell is going to be 2 pi r, give us the length and the height, and then the width, which is dx. And the shell method, we're just going to add a bunch of those together. Instead of writing like the formula we have on that side, what I do here is just going to be 2 pi, the radius, I just use a capital R, the radius, and then the height, and then the width. Uh, 2 pi r, the height, the width in this case could be dx or could be dy, depends on the axis of rotation. So we're just going to go with this as a limit from a to b, right. And a to b, yeah, right. Let's take the 5-minute break. When we come back, we do one example. I mean, a few examples. So we continue at 9:10. So we continue. So the radius is exactly like what we have earlier, from the axis rotation to, but this time it's not to the edge, it is to a point in the middle. So the first example is not particular nice, but let's see. Bounded by sine x squared, the x-axis, and the vertical line. X equal to square root of pi over 2. Find the volume. Of the solid. Generate by rotate the region on about the y-axis. This is using the shell method. Of course, we can use this method or the washer method, but in this case, we should use the shell method. Right. So the graph is over there, but let me find the rod. Right. As mentioned before, this example is not particularly nice. The next one is better. So y equal to sine of x squared, kind of like y equal to sine x. Still from 0 to 1, that is. Right. This one. Right. And then the x-axis. And then x equals square root of pi over 2. Let's say this is square root of pi over 2. Right? So we're talking about this one. Right. So the radius in this case is not going to be the radius that we have in the dish on the washer method. So kind of confusing if we not paying attention. So a route rotate about the y-axis. Now this time we do not slicing the x-axis, we're using the shell method. So we just have the axis in that direction. What we do is we just grafting around it. So there's one shell, and when we're done, we get another one, and we just grafting around it, and we just keep doing that. So shell is just grafting around, and we from the inner shell to the big shell. Now think about this. If it is a shell, it's like this. The thickness of a shell, this thickness, is going to be in that direction, right? So if we talk about the thickness is corresponding to each one of this, meaning that it is going to be dx. So if it is in the slicing, most important in the slicing, we slice the axis of rotation. If we slice the axis of rotation, so it will be the dy or dx is parallel to it. Now on this one we wrap around it, so whatever the dx or dy have to be perpendicular to the axis of rotation. So the width is perpendicular to axis of rotation. So that one, it is going to be dx. It is going to be dx. And the limit for x from 0 to square root of pi over 2. Right. So we have x. We know that had to be dx. And then we have the limit for x. Now determine the radius and the height. Notice that this is not the radius in the sense of the this and the Watson method. This one, the radius, kind of strange. We're not going to talk about that. Right. Right. So now we wrap around this, right? If we have to draw, I just draw the parallel line to the axis of rotation on the region. That gives us the height. And we just will wrap around it. And this is going to be the radius. Right, so the shell, we draw the line parallel to the axis of rotation, and then we just will wrap around it. So in that case, what is the radius? Now that is, like I said, a bit more difficult, but that is the radius. In general, if this is x, we just say that is the x values. So the radius is actually just x in this case, because that point is equal to x. X could be anywhere from 0 to square root of pi over 2. And the height is going to be from that 0 to the function. So we just have sine of x squared. So the volume integral from 0 to square root of pi over 2 pi x sine of x squared dx. Right. So like I said, on this one, the difficulty is we don't find the radius from the axis rotation out. What we do is first we draw the horizontal the line parallel to the axis of rotation, and then we form a cylinder by revolving that line around the x-axis, in which case we have the height and the radius. So that is the difference that what we have in the dish and the washer method. Since this is a kind of the best example, I think we should have a better example, and that so we get the better idea of what we should do. But that's how we set it up. We do a lot of examples, including comparing with the dish and the washer method we have earlier. D. By the way, if you have any question and it is in a little bit more general and not in particular related to the note. So if you don't want to type in the chat, you can always send me an email. I check email during the break. Just leave it like that. Right, and now let's just graph it first. We have y equal to square root of x minus 2. And y equal to 2. I guess I have to zoom out. Right. We'll talk about this region. Let me zoom to that particular part. Zoom box. Oops. Upper left and lower right. That will do. Right. And revolving around the x-axis. y equal to square root of x minus 2. If we put in 0, square root of negative 2, that imaginary, doesn't work. So it have to be at least 2. Two, 4, 6, and 8. Right. And then if we put 3, square root of 3 minus 2, square root of 1 is 1. 2 and 0, 3 and 1. And put 5 in, it's not even. So try 6 to get a nice and even number. Square root of 4 is 2. So 6 and 2. And then y equal to 2. And this is in the first quadrant, so it's going to be in that corner. So it is bounded by the positive and the x equal to 0, y equal to 0. So we're talking about this one. Now this one rotates about the axis of rotation of x equal to the x-axis. Right. Before we do this point, obviously 2 and 0, and this point here, x equal to 6, y equal to 2. We're talking about that region here. Right. Here is bounded by that part of the graph. Now we rotate. Right, now, again, this one we use the shell method also. We can also use the disk method. In this case, could be complicated. The shell method is a lot easier. Right, now, axis of rotation is like this. Now we rotate around the axis of rotation. So we're going to graph around it. So if we graph around this, the thickness of the paper, the thickness of a shell is going to be perpendicular to. So when we graph around, that is the thickness of a shell, and it is always perpendicular to the axis of rotation. So this problem is going to be a dy. Again, always perpendicular to the axis of rotation. So the slicing method, it is parallel to, we slide the axis of rotation. The shell, we wrap around it. So the thickness is perpendicular to the axis of rotation. Right, so the most important in the shell method is in order to determine the radius and the height, we have to draw a line that is parallel to the axis of rotation to form a shell. So what I do is I'm going to draw a line. Always have to draw a line that is parallel to the axis of rotation. With that, when we rotate, we will have a shell. Right? So it's a shell like that. The thickness, of course, is dy perpendicular to axis of rotation. Right? So rotate like that. Or you can, if you're not sure, rotate the paper like this. Anyway. Now, what is the height and what is the radius? Now, it's not the height and the radius is of this cylinder, right? The height, obviously, is this is the height, which is that one. And the radius is the radius of that cylinder also. So it's going to be this. And you say, what is that? Because then we don't know. We could choose any shell, right? We could choose the one with any radius. Could be bigger, could be smaller than this cylinder here. So in that case, we just say it, because we're going to use dy, this is going to be y. Right, so first, the same method about the x-axis perpendicular to the axis rotation, that is dy. So we're going to start with dy. So 2 pi radius times the height. This is going to be dy. And the limit for y from 0 to 2. The y values between 0 and 2. So easy to determine the limits. Now, what will be the radius? The radius is of that cylinder is going to be just y. And it could vary anywhere from 0 all the way to 2. You see, the height could be very small cylinder or very big cylinder, but cannot be more than 2. So the biggest cylinder we can have is a cylinder of the radius 2. The smallest one of the radius 0. So we'll let that radius be y, since we choose y to be from 0 to 2. Right. The height. The height is going to be this, which is bounded from the left by 0 and bounded on the right by this curve. Notice that it has to be as the function of y. So we cannot use this function. Let's square both sides. So x equal to y squared plus 2. And we have to use the function in terms of y, because we have dy, and it is on the right by y squared plus 2, and on the left by y x equal to 0, so just minus 0. And put this together, we will have integral from 0 to 2 pi y squared plus 2 dy. Right. If we want to do this by hand, actually we do that regardless of using the calculator or do it by hand. We check out the constant whenever possible. Then just multiply them out. It should be very simple. Right, I'll just use the calculator for that part. Math number 9. Instead of y, we just use x, because it's a lot easier to type x than to type y. So that's going to be 8. And we're going to stick the 2 pi and then 8, so 16 pi. The answer for this problem, usually whenever possible, we keep that in terms of pi. Right. Now, again, the characteristic of a shell method is we have to draw a line parallel to the x-axis in the region, and then we rotate that to determine the radius and the height. This radius kind of different than the radius we have for the dish and the washer method. Right. Next, we do the comparison between the dish and the washer method. I mean, dish or washer method versus the shell method. Right. Even it is set a summary, but look like there's an example. So we do dish and washer method. Now this one we don't have a particular function, so we just say let this region be, let's say, y equal to f of x, or it can be written as x equal to g of y, which is this function here. This and washer method rotate about this axis, x equal to 6. Right, how do we set it up? The height, like that, for the shell method, we draw a line that is parallel to the axis of rotation, and from the region, that will be the height. It will be from different of those two functions. In that case, from that function to this function. We'll see, we do a lot more example, but for the shell method, we always draw the line parallel to the axis of rotation to determine the height. Right. This washer method. Now, This Western method, usually also called the slicing method. So when we slice it, we slice the axis of rotation. So if we use this Western method, this is going to be dx. Where that is the dish or the Western, it's going to be pi radius square minus little radius square. And if it is x, from here, look like it go from 0 to 2. Now, for this Western method, we need two radii. The big radius and the little radius. The big radius is from the axis of rotation to the furthest point away on the region. So the big radius in this case is that one. How do we determine this distance? Again, it's kind of like the region of the area between two curves. It is bounded below by this one and bounded above by that line. So the line above is y equal to 6, sorry. Bounded above by y equal to 6 and bounded below by y equal to f of x. Yeah, that curve. Right. So above minus below is the r. Now the little radius is bounded above by 6, bounded below by 5, right? So it's 1. So the big radius from the axis of rotation to the farthest point away of the region. Of course, when we talk about distance, it has to be perpendicular. It cannot just go to this point. It cannot do that. It has to be straight. So that is the first point away from it, r6 minus the function, and then little r6 minus the inner function. So we have those two. Just say 6 minus f of x squared minus 1 squared dx. So that is this method. Now do the comparison with the shell method, and I hope you see the difference of the two. Two, 4, 6. The function here is y equal to f of x, or x equal to g of y. This line is y equal to 5. And the axis of rotation, y equal to 6. Now the axis of rotation is this, but this time it is the shell method, so we're going to wrap around a cylinder like this. So in order to visualize that, whenever we have the region, always draw a line parallel to the axis of rotation, but have to be in the region. So parallel to the axis of rotation is this. And then we wrap around using that radius. So equidistant away from it. Kind of right here. So we're talking about this cylinder. Talk about that shell. Right. So whenever we draw a line that is parallel to the axis of rotation in the region, that automatically is going to be the height. So just draw a line parallel to the axis of rotation and in the region. That gives us the height. And the radius will be from the base of the point. This is going to be the radius. But before we do any of that, the cylinder here is like that, wrapping around the axis of rotation. So the thickness of the shell is dy. So this problem, it is going to be a dy problem. (2.rh) and dy, where the y in this region looks like it goes from 1 to 5. Determine the height. The height is that region. So it's bounded on the right by the curve and bounded by the left by the line. So we will say it is by a function of y to g of y minus 0 on the left. G of y on the right, again we have to use the function of y. So that's just g of y. Now the radius is difficult to determine here. Now, like I said, kind of difficult. Now if we think about this, here is 0, y equal to 0. If we're talking about from the base of the cylinder, that point go down to that. We talk about this distance here. That distance is the y values. So that y values can vary from 1 to 5, right? So that is the y values. From a point, the end point of the line that we draw is going to be y. So that is y. And we have 6 above minus the y. So when we're talking about the radius actually is going to be this. The radius is equal to 6 minus y. The whole thing is 6. Take away the y values, give us 6 minus y. So it's always in this problem, when we talk about the radius, we always have to have either x or y in this case. X or y is from that point to 0. That gives us y. But the actual radius is from the 6 minus y. So when we talk about this cylinder or this shell, the radius is that, which is 6 minus y. And then put everything in the integral. From 1 to 5, 2 pi radius 6 minus y, and then the height g of y dy. So just like this on the shell method, the first thing we need to determine is that going to be dx or dy. And when we have dx and dy, we can determine this or washer method or shell method on the components, either the big R, little r, or the radius and the height. So we have quite a few examples here. Right. So what happens if we rotate around the vertical axis? Right. So let's say we have the same region, but we rotate about different axes. So I'm going to draw this two again. Okay, y equal to f of x or x equal to g of y. We don't know that. Y equal to 5. This time we rotate about this axis. Right. Now, first, this washer method, slicing method. Let's cut the axis of rotation into a bunch of slicing. So this obviously going to be dy because that's vertical. So dy. And the y values go from 1 to 5. This washer method from 1 to 5 pi r square minus little r square dy. Right. By the way, the vertical line is x equal to 3. Right. Now determine the big radius. The big radius going from the axis of rotation to the outer edge of the region. That is the big radius. So what's that equal to? Now consistently the big radius is always that. So it's going to be 3 or 3 minus 0. Right. Now the little radius from the axis of rotation to the closer edge. in this case that R. And it's going to be on the right by 3, on the left by x equal to g of y, so 3 minus g of y. So big radius, small radius. So that is this or the Watson method. Four. Shell method. Have the same thing. Rotate about the x equal to 3, but this time we use the shell method. So for one solid of revolution, we can do both, either the this or the Watson method, or could be a shell. One is slicing, one is wrap around. Yes. Right. Now, the same method. First of all, is that the x or dy. Now, if we graph around the axis like this, a shell is like this. So, it's always draw a line that is parallel to the axis of rotation, which is that, which is the height. So always draw a line parallel to the axis of rotation, and then we rotate about the axis of rotation. So it's always draw a line parallel to the axis of rotation. That gives us the height. And that line, of course, have to be in the region. You cannot just draw any random line. Right. And also, if that is the cylinder, the thickness of a shell is going to be dy. I mean, the x, because that is horizontal. Right. So the volume by shell, 2 pi RH, and we use the x, and x for this problem go from 0 to 2. Right. What is the radius? Now, kind of very difficult to determine the radius here. See, it's always the base, one end point of the height, one end point of the cylinder, that point to the 0 line, so that is going to be the x values. The x value is this much, that much. Now the radius is actually from the axis of rotation to the height. That is the radius. So it's going to be 3 on that side, and then on that side it's going to be x. So the radius is going to be 3 minus x. Yeah, because it goes from 0 to that, whatever that point is. So that's 3 minus x. And the height will be this, bounded above by 5, bounded below by the function of x. So use the function of x. So the volume is equal integral from 0 to 2 pi, radius 3 minus x, and the height 5 minus f of x. This one is dx. So again, that two distinct different methods. One of them we draw big radius, little radius, and one of them we draw the line parallel to the axis of rotation. So we will form a shell. Right. Let's write a note. First, for this Watson method, the dx or dy is parallel to the axis of rotation. Meaning we're going to slicing that, and the x or dy will stacking up along the axis of rotation. For the shell method, the x or dy is perpendicular to axis of rotation. Right, so first, and for the dish or the Watson method, we need the big R, little r, and now just write the formula for the dish or the Watson. And then either dx or dy here. And then for a shell method, of course there's the limit to be determined with x or y. The shell method, 2 pi r h, again the x or dy, limit to be determined. Right. Let's take another 5 minutes. We continue at 10:10. Excuse me. Right. Before we continue, just want to talk about the schedule real quick. This is what my plan was for the course. So those are the sections we need to cover, and originally I thought we could cover that in 4 days, way behind schedule. So in that case, look like we don't have class time to dedicate for review, so we have to try to go as much as we have for 5 days, and the test will be right here. We will not have any class time for testing, obviously, so the test will be whenever you want to take it. It's fine, but I recommend it's going to be the end of this week, sometime this weekend. I probably have to have one day, maybe Saturday. It is optional. If you want to, if you have any homework question, you can ask during that time, or if not, we can go over the review question. So that may be this Saturday, and the test one may be this Saturday. And if we're behind, then we have to pick it up later. But for now, that's what we have. Just way behind schedule. But in terms of another pace, in terms of pacing, this kind of problem, because we have to raw, so it takes a lot of time to actually raw and then to do the problem. Later on, we don't have to raw as much, especially in chapter 8. For the rest of the section, except chapter 12, we might need to raw a little. But in terms of the note, I actually complete the note already. That is 130 pages, and I plan to go over that on 20 days. So that probably, let's say 140, so about 7 pages of notes a day. So in that case, we're not that far behind as far as the pacing goes. So it's not that bad. So look like we constantly have 7 pages a day. And of course you can check the note I post on eCampus. We probably write on pace for that. So in terms of section, we're a little bit behind, but in terms of the content, probably we write on pace. Right. What we have now, we will have a question like this on the test for sure. One region R using both dish and shell, dish or washer and then shell. We have to use both methods. In that case, we can compare the answer nicely. First, let's write the prompt. Let the region R be bounded by y equal to x cubed, y equal to 0, y equal to 8, sorry, and x equal to 0. Find the volume when R is revolved about the x-axis. And we're using both shell and dish and washer method. So just divide the page in half. So we just do that. So here we use the dish and washer method. And then we use the shell method. Usually we just need to draw one, but I'm going to draw the region 2 times. Y equal to x cubed, that's easy. Choose some value for x and then we can graph. But it's going to be very skinny. Let's see. Y equal to x cubed. Zero cube is 0, 1 cube is 1, 2 cube is 8, 2, 4, 6, 8. A little off there, but that's fine. So this is y equal to x cubed, y equal to 8, and x equal to 0, of course, is the y-axis. Now, this one rotates about the x-axis. For dishwasher method, first determine, or the shell, is that going to be the x, or is that going to be y? Is that going to be the x, or is that going to be the y? So axis of rotation is this one, so we're going to slice the axis of rotation, so that's going to be the x, parallel to the axis of rotation. So that's the first thing we determine. It's going to be dx. So pi big R square minus little r square, this is going to be dx. And the x, if we're talking about the region, it's going to be 0 to 2. Right? So the first thing determine the x or dy, and then the limits. That is easy. Usually when we draw the region, it should be just like that. Now, big radius and little radius. The big radius is from the axis of rotation. You have to use different colors here. From the axis of rotation to the furthest point on the region. To the outer edge. We go from 0 on the way to 8. So the big radius, the one above 8, the one below 0, 8 minus 0, or just 8. That's the big radius. How about the little radius? The little radius is from the axis of rotation, the x-axis, to the inner edge. So to the inner edge, which is a function of x. So it's x cubed is above, 0 is below. So just x cubed. So put those two together, we have the volume is equal to integral from 0 to 2 pi big R square h square little r square x cubed square. So that gives us 0 to 2. We can always take the pi outside, and that is 8 minus x to the 6 dx. Right, let's put in the calculator and see what we have here. Math number 9, from 0 to 2. Ignore the pi, don't put the pi on the calculator. Is that a square? R square, right? 64, or just a square, minus x to the 6 dx. Right, okay, we have a fraction out of this. 768 over 7 pi 768 over 7. Right, let's keep that as the answer. So using this dishwasher method, that's what we have. Now, same thing, but using the shell method. Sorry, I want to put my hand on the way. I hope by doing a problem 2 different ways you can see the difference, draw the contrast and similarity between them. Actually, there's not much similar. Much better this time. Y equal to 8. Shouldn't a square be 0? No, I mean I just put inside the integral. So the radius square, so 8a square. Yeah, when you integrate, that will be 64x. I mean, if we do this by hand, 64x minus x to the 7 over 7 from 0 to 2. Yeah, and when we put in here, this is what we have. Yeah, but oh, I see. The big radius is going to be 8 because the axis of rotation is here. If the axis of rotation is at 8, then the one of the radius is equal to 0, right? But the axis of rotation is here. Yeah. So from the axis of rotation to the outer edge, it's always 8, constantly equal to 8. The little r is not constant. It could be this, or higher, or smaller. Those are little r. Right. Now, show the same region here. And show, is that going to be dx or dy? So, the axis of rotation is here. And so we're not slicing or dicing anymore. We're wrapping around it. And the width is going to be dy. It is perpendicular to the axis of rotation. So the same method, it is going to be dy. Two pi r h. And the y values going from 0 to 8. Because that point 2 and 8. So we go from 0 to 8. Right. Now just need to determine what is r and what is h. What is r and what is h? Right. So for that, we have to draw the line that is parallel to the axis of rotation, which is this. Draw a line parallel to it. That is the height. And then we rotate about the x-axis. So when we rotate, we have that cylinder, right? So the height is just parallel to the axis of rotation. So we form a shell like that. So let's determine the height. We can always, whatever we do has to be a function of y. So y equal to x cubed equivalent to x equal to y cubed. Cube root of y, sorry. Yeah. X equal to cube root of y. And for that height, on the left is by the cube root of y, and on the right 0, right? So the height is on the right by cube root of y, and on the left 0, or just cube root of y. And then the radius. And the radius always, the endpoint of the height go to the 0, the line 0, that is the y values. And it just happened to be the r, because that also the distance from the axis of rotation to the shell. That's just y. Yeah, this distance will be 8 minus y. Right. So bottom line, when we put things together, that will be v equal to 0 to 8, 2 pi. The radius is y. The height is the cube root of y dy, which, if we factor out the 2 pi, y times cube root of y, this y to the first, y to the 1/3. So it's y to the 4/3. Right, see what that is. I'm just going to use x. It is a lot easier to type than y. Right, so we have that. Wait. Right? Now, we have to multiply by 2. Because there's 2, and then we leave the pi out later. Multiply by 2. Can we change the fraction? So the answer is going to be pi, and then 2 times the integral, 768 over 7. If we compare the answer, they should be the same. So, hope you see the contrast between the dishwasher method and then the shell method. The dishwasher parallel to the axis rotation. The shell perpendicular to it. So one of them is dx, one of them is the other one is dy. So it's like that. And then the shell 2 pi r h. Dishwasher big R square minus little r square. Determine all of those, and we should have it. The answer for those two should be the same because we have the same volume. Right. Have any question on this too? Yeah, I have to say out of all this, the big R, little r, and the h easy to determine. Usually the r in the shell method is kind of difficult to see. So what I do is I just take from the end of the height, go to either the x-axis or the y-axis. That will be the y or the x, depends on our problem. Since this is y, we go to the x-axis. That is the y. Now, is that the radius? If that is, then it's good. If it's not, I have to do something with it. We will have that in the next example. Yes, like I said, the R is kind of the most difficult out of all of this thing to determine. So we take the point, go to the x-axis or the y-axis. That gives us the x or the y values. Since this one we use dy, so we find out the y values is from that point to 0. So that is y. And it just happened to be r, so that equal to r. Then we have to do another example so we can see how to determine r in the same method. On this problem, on the previous problem. Right. The h is we have to draw that parallel to the axis of rotation, and it just happened to be horizontal, so the function on the right minus the function on the left. Or on the previous problem, the height, it is vertical, so it's bounded above and bounded below. The big R or the little r is, and the h kind of set up the same way. We have to draw it out, and then above minus below, on the right minus the left. Just find the distance. It's always like that. So above by 5, below by g of y. It's not a very good one, especially we don't have the function. So this is the height. It is bounded on the left by this function, and the right by this function. But both of them have to be in terms of y. So the function on the right is cube root of y. Yeah, it looks arbitrary because you can draw that height, or we can draw the height as long as this is parallel to the x-axis by the axis of rotation. So this could be the height as well, or this could be the height. Either way, when you draw it parallel to the axis of rotation, it is bounded by the left by the red, y equal to x cubed, or x equal to cube root of y, and it is bounded on the left by the y-axis, or x equal to 0. Yeah. So you just draw the horizontal line, draw the line parallel to the axis of rotation on the region. See what is the bound on the right, what is the bound on the left, and subtract them. We should find the h. Yeah. So any of those can be h. And then back to the r. The r, take the endpoint of one of the h that you set up. Go to the x-axis or go to the y-axis. That gives us the x or the y values. So if this is the point, that gives us the y values. And just happen to be the same as the axis of rotation, the same as the radius. So in that case, yeah. So let's go to the next problem. If it helps at all, when we set up those two, at least one thing we sure, the answer for those two should be the same. Doesn't matter this or the washer method, we should have the same volume. Yes, sometimes we have to find the inverse for y. So if this is y equal to x cubed, we have to solve for x in terms of y. So we take the cube root on both sides. So we have cube root of y equal to x. Cube root and cube cancel out. So x in terms of y or y in terms of x will be determined by, do we use dx or do we use dy? Have to be the same variable. Yeah. Sometimes we have to find the inverse to match the variable that we're using. If this is dy, all the variables must be y. If it is dx, all the variables must be x. So that's why the first thing we do in this problem, I ask you, should we use dx or should we use dy? So that's why we need to know, do we need x or do we need y? Right, y equal to x squared, y equal to 2, and y axis. Right. Yeah, on this one we just graph it by hand. Right, slow down, graph y equal to x squared, y equal to 2. Good. Oops. Yeah. So we're talking about that region here. Ah, yes, that's fine. One, 2. Right. Y equal to 2. That's easy. Just do that first. And then y equal to x squared. When x equal to 0, y equal to 0. X equal to 1, y equal to 1. And when y equal to 2, because that's square root of 2. So we have 2 squares, 2. Right. Here we have y equal to x squared. Just in case we might need the inverse later. Y equal to x squared, the inverse. Or x equal to square root of y. But interchangeable. We use both of them. Because right now we don't know if we use x or y yet. But we know the region is that. Alright, now axis of rotation is 3. X equal to 3, that is. Now, is that going to be dx or is that going to be dy? My first question is always like that. Now, the axis of rotation is that, so we're going to slide, because when we slide like that, it is dy, and as always, the dx or dy have to be parallel to the axis of rotation. For the dish or washer, for shell, it's going to be perpendicular, so this is going to be dy. Right? Now when we know it's dy, the r and r here has to be in terms of y, cannot be x in it. And also the limits from 0 to 0, 0, 0 to the point x equal to square root of 2, y equal to 2. So for limit for y, it goes from 0 to 2. Now the big radius. The big radius is from the axis of rotation, that one, to the outer edge. Just take any point on there and go to the outer edge. That is the R. And I will just say is the function on the right minus the function on the left. The function on the right is x equal to 3. The function on the left, the y-axis, or x equal to 0. So 3 minus 0 is 3. That is the big R. The little r is from the axis of rotation to the inner edge. On the right minus on the left, the one on the right is x equal to 3. The one on the left is this function. So which one do we use? Of course, since we use dy, we have to use the one that have the y as a variable. So 3 minus square root of y. That's the little radius. Right, put that in here. Take out the pi. 3 square for big R. 3 minus square root of y for little r. Right. Since we just set up the integral, that's it. On the test, if you ask to set it up the problem, then that's all we do. We can write that as 9 if you want to, but no big deal, just that. Right. So I think the dishwasher is not as difficult as the shell. is x equal to 0. Axis of rotation still x equal to 3. Right. It's first, always, do we use dx or we use dy? If we do both of them, one has to be dx, the other one is dy. So this one must be dx. But remember, dx or dy in the same method, it is perpendicular. So it's going to be dx. And the x, since we go from 0, 0 and square root of 2 and 2, it will be from 0 to square root of 2. Right. Now, the more question should be, do we use what is r and what is h? Right. In order to determine those, we have to draw in the region that is parallel to the x-axis, parallel to the axis of rotation. So, let's see about this. Could be any line, though, but we use that particular h. So the h, how do we determine that? The h is this, which is the vertical line. So what is the boundary above and what is the boundary below? Have to be in terms of x though. So we see boundary above by 2. And boundary below by this curve. And the curve, we have to use x, dx that is. So have to use, sorry, which there's an undo button. Sorry, we have to use the one with x. So we have that. Right, draw a parallel line to the axis of rotation. What is the function bounded above? What is the function bounded below? Or what is the function on the right? What is the function on the left? To subtract them. And whatever the variable is, we have to use that variable. Since this is dx, have to use x, which is this one, not that one. Sorry. Now the radius. Oh, now this is a bit more difficult. So we just pick a point on the line. Usually I use this point. It could be this point, it doesn't matter. What we do is, we're going to find what is the x values of that point. What is the x distance of that point, right? So if we go to the x-axis, this is going to be the y values. If we go to the x-axis, this is going to be x values. We use x, so we need to have x. So whatever the point is on the line, go to the x-axis, go to the y-axis. Which one is x? Oh, that one's x, because we use x, right? So if this is the x distance, here is x. Now, the r though. The r is from the axis of rotation, this line, to that point, right? This is the radius. Because this rotates about like that. I don't have enough space on this side, but it is a shell like that. So whatever point, that point is to the axis of rotation. So we need to find this r. So how do we determine r? Knowing that this is x, the whole thing is 3. If the whole thing is 3, take away x, we have r. So r is going to be 3 minus x. Once again, the first thing we determine is a point, pick a point on the line that we drew. Go to the x-axis, give us the y values. Go to the y-axis, give us the x values. Since we have the x, so we're going to stick with the x values here. Now, that point to the axis of rotation is r, so we need to find that distance r. Knowing the whole thing is 3 and take away x, r is equal to 3 minus x. And then we put everything back in here. Take out 2 pi. 2 pi. Already took that out. R. That's just right. RH and dx. So 2 pi 0 square root of 2 r 3 minus x, and then h 2 minus x squared dx. Now if we do both of those integral, we should get the same thing. So I hope that you get a better idea of how to set up r and h. Right? So kind of draw a line randomly parallel to the x-axis, parallel to the axis of rotation, but have to be within the region. And then find that distance, give us h. In this case, the function above, x equal to 2, y equal to 2, the function below, x equal to square root, y equal to x squared. So both of them have to be as a function of x. So 2 minus x squared. Right? So a function above, y equal to 2, the function below, y equal to x squared, because it has to be in terms of x. So we have that height. Now, pick a point on the height on that. Go to the x-axis, go to the y-axis. Go to the y-axis is x, go to the x-axis is y, right? That's the distance. Since we have dx, we're going to need x. And then from that point to the axis of rotation is r. And then we take 3 minus x. Right. Go back to the previous problem. I hope this might be clearer now. So we can take any point, go to the x-axis, go to the y-axis, go to the x-axis is y, go to the y-axis is x. On this problem, we don't need x, we only need y. So we know this distance is y. And from that point to the axis of rotation, that is r, which just happen to be y. So, yeah. So little big with the r here in the shell method. Other than that, it's always the function on the left, or the function on the right, minus the function on the left, the function above, minus the function below. And then the r is either we have to find x or y, depends on the problem, for a point. And then from that point to the axis of rotation, what is that? That would be r. And in this case, 3, the whole thing, minus x, give us 3 minus x, the r. Right. Obviously, this kind of problem we will take a lot more time to do than to do a problem, let's say the derivative or integral, because we have to draw it out nice enough so we can see the components of it. But other than that, we run out of time, so I have to stop here. We still have one more example. Actually, two more examples, but I think I only need to do. We have one more example. I'll do that for next time. But at least I hope you have some idea of the dish and the washer and the same method, the similarity and the differences. Yeah, one of them will be dx, the other one is dy. Right. So I will stop here. Like I said, we are way behind schedule in terms of section, but in terms of the content, it's not that bad. So the plan is we finish this section and 6.5 on Wednesday, pick up 8.1, go as far as we can, and then we finish that on Friday. So on Friday, if we have time, we'll review. If not, we have to do some different time. But look like at best, the best should be probably you will take the test sometime this weekend. But like I said, this is kind of like the online class. As long as you finish the test at the end of the semester, I'm okay with it. You don't have to take the test this weekend. Could be later, whenever you're ready. Right. So I'm going to stop here. Do you have any question before I close the stream? Right. If not, I think I'm end the stream here. Right. I'm going to end the stream here. Thank you for watching. Have a nice day.